No one was supposed to notice this planet, and that is what makes the signal so unsettling, because James Webb did not find it while hunting for life, or even for something strange, but while doing routine science exactly as planned. The universe did not shout, it whispered, and that whisper arrived as a faint distortion in infrared light, so subtle that it could have been ignored if it had appeared anywhere else. But it didn't appear anywhere else. It appeared in the atmosphere of a planet that should have been chemically silent, biologically inert, and scientifically boring. When the data first appeared on screens, it looked ordinary enough, a familiar pattern of light broken into wavelengths, the kind astronomers analyze every day. Yet as the noise was stripped away and the signal sharpened, an uncomfortable truth emerged, which was that something in that atmosphere was behaving in a way it had no right to behave. The chemistry was wrong, not slightly wrong, but fundamentally out of place, showing signs of imbalance where equilibrium should have long since taken over. On lifeless worlds, chemistry settles down, reactions complete, and gases stabilize. But here the data suggested persistence, renewal, and activity, traits that nature does not maintain for free. No alarms went off, no announcements were made, but the room grew quieter as scientists realized that this was not a glitch they could casually dismiss. James Webb was working perfectly, its instruments calibrated, its measurements repeated, its conclusions stubbornly consistent. This was not a one-frame anomaly or a statistical fluke, but a signal that survived scrutiny and repetition, which is the most dangerous kind of discovery in science. The unease did not come from the idea of alien life, because that thought was deliberately kept at bay, but from the realization that the planet itself was violating expectations. This world was never meant to be interesting. It orbited its star under conditions considered hostile by every modern definition of habitability, exposed to extremes that strip atmospheres, break molecular bonds, and sterilize surfaces. Astronomers had classified it years ago, filed it away as another example of what not to look for, another reminder that the universe produces far more dead worlds than living ones. And yet, Webb's data suggested that something was happening there, something sustained, something ongoing, something that refused to fade into chemical silence. The discovery unfolded slowly, through verification and re-verification, as teams checked for instrument error, stellar interference, data processing artifacts, and modeling assumptions, hoping the signal would dissolve under pressure. Instead, it hardened. Each new pass through the data made it clearer that the atmosphere was maintaining compounds that should not coexist under those conditions, a situation that on Earth would immediately trigger one uncomfortable word: metabolism. Still, no one said it aloud, because science is careful, and because history is littered with premature claims that collapsed under further scrutiny. But caution does not erase implication, and the implication here was simple and deeply disturbing, which was that this planet was acting alive without permission. What made the moment truly disruptive was not the possibility of life, but the challenge it posed to certainty. For decades, astronomers have relied on a framework that defines where life can exist, drawing careful boundaries around temperature, radiation, chemistry, and orbital stability. Those boundaries are not guesses, but conclusions built from physics, biology, and everything we know about how life behaves on Earth. This planet sat well outside those boundaries, far beyond the zone where optimism is allowed to survive, which is why the signal felt like an intrusion rather than a discovery. It suggested that the universe might not respect the categories we use to make sense of it, that habitability might not be a narrow corridor, but a landscape far stranger and more flexible than we imagined. The discomfort spread quietly through the scientific community, not as excitement, but as restraint. Because extraordinary claims demand extraordinary patience. Yet beneath that restraint was a shared awareness that something foundational had shifted, a settling question, which is why this planet was ever considered impossible in the first place, and how a definition strong enough to dismiss it could now be forced to bend. A question that pulls us directly into the next chapter, where we examine exactly why this world was ruled out so confidently, and why that confidence may have been our greatest blind spot. To understand why the signal felt so wrong, we have to go back to the moment this planet was first discovered. Because from the very beginning it was never considered a candidate for anything other than exclusion. When astronomers catalog new exoplanets, they do not treat each one as a mystery to be solved, but as a data point to be classified, measured, and compared against what is already known. This planet's numbers placed it firmly in the category of no, not a tentative no, but the kind of no that feels settled and final. Its orbit hugged its star too closely, bathing the planet in radiation intense enough to shred molecules and erode atmospheres over cosmic timescales. Its equilibrium temperature sat well outside the range where liquid water could persist on a surface, and water, as far as we know, is not optional for life as we understand it. The star it orbited was active and volatile, prone to energetic flares that can sterilize planets by bombarding them with high-energy particles, stripping away protective atmospheres and leaving behind barren rock. Even the planet's mass and density worked against it, suggesting either a thick, crushing atmosphere hostile to complex chemistry or a thin, fragile one unable to shield anything beneath it. There was no single disqualifying factor, but a convergence of them, stacking together until the verdict felt obvious. This was not a world on the edge of habitability, not a borderline case worth arguing over in conferences or papers. It was the kind of planet used as a teaching example of why habitability zones exist in the first place. Over the years, thousands of planets like it have been discovered, logged, and quietly ignored because science cannot chase every possibility, and patterns matter. The habitable zone, imperfect as it is, provides a useful filter, allowing astronomers to focus limited resources on worlds that at least resemble the conditions that allowed life to arise on Earth. This planet failed that filter decisively. It lived in an environment where surface water should boil away or freeze solid depending on atmospheric pressure, where radiation would damage complex molecules faster than they could form, and where chemical stability would favor simplicity, not persistence. From a modeling standpoint, it was a dead end. No one expected it to retain a complex atmosphere over billions of years, let alone maintain one showing signs of chemical imbalance. In the language of planetary science, it was dynamically and chemically uninteresting. And that confidence is important, because it shaped how the planet was treated, not just by individuals, but by the entire system of astronomical priorities. Telescope time is precious, and every observation must be justified against competing proposals. Worlds like this one rarely receive that justification, because they offer little return under existing theories. When James Webb was launched, its mission was not to overturn habitability models, but to refine them, to study promising exoplanets, early galaxies, and the chemistry of worlds already suspected to be interesting. This planet was not on that list because it didn't need to be. Its fate had been decided by physics long before Webb ever unfolded its mirrors. That is what makes the later detection so disruptive, because it didn't challenge a weak assumption but a strong one. The rules used to exclude this planet were not arbitrary, but built from decades of observation, laboratory experiments, and theoretical work. They reflect what radiation does to molecules, how atmospheres behave under stellar assault, and how energy flows through planetary systems. These rules work remarkably well across thousands of observed worlds, which is why they inspire confidence. When a planet violates them, the immediate impulse is not to question the rules, but to question the observation. This is why, when Webb's data began to suggest something unusual, the first reaction was disbelief rather than excitement. The idea that such a planet could host anything resembling sustained activity felt less like a discovery and more like a mistake waiting to be uncovered. Scientists retraced the planet's history, reviewed its classification, and reaffirmed every reason it had been written off. Its star's spectrum confirmed high radiation output. Its orbital parameters confirmed extreme exposure. Its estimated atmospheric properties reinforced expectations of instability. Every box remained checked. And yet, none of that erased the signal. The deeper scientists looked into why the planet should be lifeless, the more uncomfortable the contrast became with what Webb appeared to be seeing. This tension created a strange inversion, where the very certainty that once justified ignoring the planet now amplified the shock of its behavior. If this had been a marginal world, a planet grazing the habitable zone, the signal might have been framed as surprising but plausible. But this planet offered no such comfort. It forced a confrontation with the possibility that the criteria used to dismiss it were incomplete, not wrong in isolation, but blind to something else at work. And that realization carried a dangerous implication, because if a planet so thoroughly disqualified could still produce signals of interest, then the boundaries defining habitability might be narrower than reality, shaped more by our expectations than by the universe itself. This does not mean life exists there, but it does mean that exclusion may be riskier than inclusion, and that the universe may exploit niches we have not yet imagined. The more scientists revisited the reasons this planet was ruled out, the more they recognized how much those reasons relied on Earth as a template, an understandable bias given that Earth is the only example we have. But templates can mislead when applied too rigidly. The early confidence that made this planet unworthy of attention now felt like a blindfold, not because it was careless, but because it was logical. This is the uncomfortable position science sometimes finds itself in, where logic leads to certainty, and certainty becomes vulnerability. By the end of this reassessment, the question had subtly shifted. It was no longer just why Webb saw something unexpected, but whether the assumptions used to define expected were too narrow. And to answer that, scientists needed to look not at the planet, but at the tool itself, because before challenging decades of planetary science, they had to be absolutely sure that the instrument delivering this contradiction was doing exactly what it claimed to do, which brings the story naturally to the next chapter, where we turn our attention away from the planet and toward the telescope that revealed it, and examine what James Webb was actually designed to see, and why its observations carry such unsettling weight. Before anyone could even begin to speculate about what the signal might represent, scientists had to confront a far more grounding question, which was whether James Webb itself could be trusted to see what it claimed to see, because in science, the credibility of a discovery lives or dies with the reliability of the instrument that reveals it. James Webb was not designed to chase sensational discoveries or hunt for life directly, but to read the universe with extraordinary patience and precision, especially in wavelengths of light that human eyes can never perceive. Unlike earlier telescopes, Webb does not primarily observe visible light, because the deepest and oldest signals in the universe are not visible at all, having been stretched by cosmic expansion into the infrared, where information survives but only for instruments sensitive enough to catch it. This design choice was not aesthetic, but essential, because when light travels across billions of years of expanding space, its wavelength elongates, shifting from energetic visible bands into faint infrared signatures that carry the chemical fingerprints of distant worlds. Webb was built to live in that faint domain, operating far from Earth's heat, cooled to near absolute zero, so its own thermal radiation would not contaminate the signals it was designed to measure. Its instruments were engineered not just to see distant objects, but to break their light apart with exquisite detail, allowing scientists to identify specific molecules in planetary atmospheres by the precise way they absorb and emit infrared radiation. This is not guesswork or inference layered on hope, but spectroscopy, a method so reliable that it allows astronomers to determine the composition of stars and planets across unimaginable distances with confidence grounded in physics tested in laboratories on Earth. When a planet passes in front of its star from our perspective, a tiny fraction of the star's light filters through the planet's atmosphere before reaching Webb's mirrors, and that light emerges altered in ways that reveal which gases it encountered along the way. Each molecule leaves a unique imprint, a missing or dimmed slice of the spectrum that functions like a barcode, unmistakable when measured cleanly. Webb's strength lies in its ability to measure those barcodes repeatedly, reducing noise, eliminating interference, and distinguishing real signals from artifacts that once plagued earlier instruments. This is why Webb represents such a leap forward, because it doesn't rely on one fleeting observation, but on consistency over time, returning again and again to the same target to confirm what it sees. When Webb observed this planet, it did not do so casually or incidentally, but as part of a carefully designed observational sequence intended to characterize atmospheres with rigor rather than imagination. The data pipeline Webb uses is conservative by design, stripping away assumptions, correcting for stellar activity, instrument drift, and background contamination before delivering results to scientists who are trained to distrust anything that looks too exciting too quickly. This matters deeply because extraordinary claims are not born from excitement, but from stubborn data that refuses to disappear under scrutiny. In this case, Webb's measurements were not isolated spikes or ambiguous curves, but clean, repeatable features that aligned across multiple observations, each reinforcing the same conclusion that the planet's atmosphere contained chemical signatures that should not persist under its known conditions. Scientists examined the star itself, ensuring that stellar flares or variability were not imprinting false signals onto the data, a common concern when observing active stars. They modeled the planet's orbit repeatedly, confirming that the transit geometry was correct and that the atmospheric signal was not being distorted by viewing angle or instrumental bias. They ran simulations to test whether temperature gradients, cloud layers, or pressure effects could artificially produce the observed features, hoping to find a natural explanation that would dissolve the tension. Instead, each layer of analysis strengthened the signal's credibility, narrowing uncertainty rather than expanding it. What made this especially unsettling was that Webb had observed countless other planets under similar conditions without producing such anomalies, which ruled out the possibility that this was a systematic flaw affecting all observations. This planet was behaving differently, not because Webb was unreliable, but because the planet itself was different in a way that mattered. The telescope's reliability became the foundation of the discomfort, because once that foundation held, the implications became unavoidable. James Webb is not an experimental prototype or a fragile first attempt, but the culmination of decades of engineering, testing, and redundancy, designed specifically to avoid exactly the kind of false positives that skeptics might hope for in moments like this. Its instruments cross-validate each other, its observations are independently processed by multiple teams, and its results are scrutinized relentlessly before being shared. This means that when Webb consistently reports something unexpected, the burden of doubt shifts away from the telescope and onto our understanding of the universe it is observing. That shift is subtle but profound, because it marks the moment when a discovery stops being a curiosity and starts becoming a problem. Scientists do not fear problems, but they approach them cautiously because problems force revisions, and revisions reshape entire fields. In this case, Webb was doing exactly what it was meant to do, revealing chemistry in an atmosphere that models said should be simple, stable, and uninteresting. The fact that Webb was not designed to search for life, yet still detected signals that demanded explanation, made the situation even more uncomfortable, because it meant the discovery emerged from unbiased observation rather than hopeful targeting. This was not a case of scientists seeing what they wanted to see, but of being confronted with data they were not looking for and did not know how to comfortably explain. The strength of the telescope became the weight of the evidence, because the more Webb proved its reliability, the harder it became to dismiss the signal as error. This forced a shift in the conversation, away from questioning the instrument and toward questioning the interpretation, and then toward questioning the assumptions that guided interpretation itself. At this point, the story reaches a quiet but critical threshold, because once confidence in Webb is secured, the mystery no longer belongs to technology but to nature. The telescope fades into the background as a neutral witness, leaving scientists face to face with a planet that is behaving in ways they did not predict. And with the instrument validated and the data standing firm, the narrative can no longer avoid the next step, which is to look directly at what Webb actually detected in that atmosphere, to examine the specific chemical signatures that triggered concern, and to understand why their presence together represents a contradiction that cannot be ignored, a contradiction that pulls the story forward into the next chapter, where the chemistry itself takes center stage and the mystery deepens from curiosity into genuine unease. When scientists finally allowed themselves to look directly at what James Webb had detected, rather than how it detected it, the discomfort deepened, because the chemistry revealed in the planet's atmosphere did not merely raise questions, it violated expectations in a way that felt structurally wrong. The signal was not a vague suggestion or a weak anomaly hiding in the noise, but a clear pattern etched into the spectrum of light, a pattern that pointed toward the presence of gases that should not coexist for long under the planet's known conditions. In planetary atmospheres, chemistry tends to move toward balance because reactions proceed until energy is minimized and stable configurations dominate, leaving behind quiet, predictable mixtures that change slowly over time. On lifeless worlds, this process is ruthless, stripping atmospheres down to combinations dictated by temperature, pressure, radiation, and gravity, with little room for sustained imbalance. Yet the spectrum Webb returned told a different story, one where certain molecules appeared together in quantities that should have destroyed each other or collapsed into equilibrium long ago. This was not chemistry frozen in a rare moment, but chemistry that appeared persistent, as though something were actively maintaining it against the natural tendency toward stability. On Earth, this kind of persistent chemical imbalance is one of the most reliable indicators of biological activity, because life is essentially a machine that feeds on disequilibrium, constantly pushing chemistry away from balance to extract energy and sustain structure. The presence of such imbalance elsewhere does not prove life, but it immediately demands explanation, because non-living processes capable of sustaining it are rare and tightly constrained. What made this case especially unsettling was that the planet's environment offered few obvious mechanisms capable of performing that work. The temperature profile suggested conditions that should either drive reactions to completion or prevent them from occurring efficiently at all. The radiation environment should have broken complex molecules apart faster than they could accumulate, favoring simpler, more stable compounds instead. And yet the spectral fingerprints showed complexity, persistence, and interaction. Scientists examined the specific gases carefully, not with excitement, but with caution, because every molecule carries implications about energy flow, sources, and sinks. Some gases are easy to explain abiotically, produced by volcanic activity, photochemical reactions, or interactions between a planet's surface and its atmosphere. Others are far more suspicious, because they tend to react quickly unless continuously replenished. When such gases appear together, the suspicion intensifies, not because life is the only explanation, but because it is one of the few known processes capable of sustaining such a state over time. In this case, the combination was wrong enough to feel intentional, but ambiguous enough to resist immediate interpretation. Scientists found themselves in a familiar but uncomfortable position, aware that the signal resembled something meaningful, yet unwilling to label it prematurely. They ran models to test whether exotic chemical pathways could produce the same result without invoking biology, exploring reactions driven by extreme ultraviolet radiation, unusual atmospheric circulation, or rare catalytic processes on mineral surfaces. Some models could approximate parts of the signal, but none reproduced the full pattern without resorting to conditions that themselves seemed unlikely or unstable. Each attempted explanation reduced the mystery slightly, but left behind residues of doubt that refused to dissolve. The deeper scientists went into the chemistry, the clearer it became that this was not a simple case of misinterpretation or oversimplification. The atmosphere was behaving dynamically, as though shaped by ongoing processes rather than frozen remnants of formation. This raised the unsettling possibility that the planet was not merely holding on to an unusual atmosphere, but actively cycling it, a behavior that requires energy input and regulation. Regulation is not exclusive to life, but it is rare without it, especially under harsh conditions. The signal forced scientists to consider whether their expectations about atmospheric chemistry were too Earth-centric, shaped by familiar examples, rather than the full range of what physics might allow. At the same time, they had to acknowledge that Earth's chemistry is the only proven template for life, and ignoring its lessons entirely would be irresponsible. This tension defined the moment, pulling interpretation in two directions at once, toward caution and toward curiosity. The phrase biosignature hovered at the edge of discussion, carefully avoided in public statements, yet impossible to fully suppress in private analysis. A biosignature is not proof of life, but a pattern that suggests biological influence. And the danger lies in how easily that suggestion can be misunderstood or overstated. History has taught astronomers to be careful, because false alarms erode trust and distract from genuine discovery. This caution shaped every sentence written about the signal, every graph shared, every word spoken in presentations. Yet even careful language could not fully hide the significance of what Webb had revealed, because the chemistry itself was doing the speaking. It was telling a story of imbalance on a world that should have been chemically quiet, of persistence where decay was expected, and of complexity where simplicity should dominate. The realization settled slowly that the signal did not demand belief in alien life, but it demanded humility about our definitions. Habitability had been treated as a narrow gate, a specific range of conditions under which life might survive, but the chemistry suggested that life, or something acting like it, might not be constrained to those gates alone. The universe might allow for metabolic-like processes under conditions we have not yet explored or even imagined. This idea was both thrilling and dangerous, because it threatened to blur the boundaries that keep scientific claims grounded. The task then was not to leap toward conclusions, but to stress test the signal itself, to see if it could be explained away through error, coincidence, or rare but lifeless chemistry. That task became the focus of intense scrutiny, because before rewriting textbooks or redefining habitability, scientists needed to be absolutely certain that the signal was not an illusion produced by imperfect data or overinterpretation. And so the story shifts again, away from what the chemistry might mean and toward whether it can be trusted at all, because the next step in this unfolding mystery is not imagination, but skepticism, as scientists turn their attention to the possibility that the signal itself could be false, misleading, or incomplete, a question that leads directly into the next chapter, where every alternative explanation is tested with relentless care. Once the initial shock of the chemistry subsided, the scientific instinct to doubt took over completely, because no matter how intriguing a signal may appear, science survives by trying to destroy its own discoveries before the universe has the chance to do it for us. The first and most obvious question was whether the signal was real at all, because history is full of discoveries that collapsed under closer inspection, not due to bad intentions, but because nature is complex and instruments are imperfect. Scientists began by interrogating the raw data itself, not the cleaned, processed versions that make patterns easier to see, but the messy, noisy measurements where false signals often hide. They searched for subtle biases, detector artifacts, calibration drift, and thermal interference, any trace that could suggest the atmosphere was being misread. James Webb's instruments were pushed against their limits, retested against known targets, and compared with independent observations to ensure that the spectral features were not a byproduct of how the telescope reads infrared light. The results were frustratingly consistent. The same features appeared again and again, refusing to vanish no matter how aggressively the data was reprocessed. Attention then shifted to the star itself, because stars are not passive backlights, and their activity can imprint false atmospheric signals onto planetary spectra. Stellar flares, spots, and magnetic cycles can distort light in ways that mimic chemical absorption, especially around active stars known for violent behavior. Scientists modeled the star's activity in detail, cross-referencing historical observations and monitoring variability during planetary transits to see if stellar noise could explain the anomaly. While the star was indeed active, its behavior did not align with the timing or structure of the detected signal, and the chemical features persisted even when stellar interference was mathematically removed. The next suspect was geometry, because transit spectroscopy depends heavily on how light passes through an atmosphere, and small changes in angle or limb effects can exaggerate or suppress certain features. Orbital models were refined, transit depths recalculated, and atmospheric thickness profiles adjusted, all in an effort to flatten the anomaly into something ordinary. Instead, the anomaly sharpened, becoming more difficult to ignore. Scientists then turned to the possibility that they were seeing a chemical illusion, a rare but purely abiotic combination of gases produced by exotic but lifeless processes. Planetary atmospheres can be shaped by volcanic outgassing, photochemistry driven by stellar radiation, surface atmosphere interactions, and internal heat leaking from planetary cores. Each of these mechanisms was modeled in isolation and in combination, pushing parameters to extremes to see if they could reproduce the observed chemistry without invoking anything resembling biology. Some models came close under very specific conditions, but those conditions required fine-tuning so precise that they felt improbable rather than explanatory. Worse, many of those scenarios predicted additional chemical signatures that Webb did not see, creating new inconsistencies while trying to resolve the original one. This pattern repeated again and again, with each proposed non-biological explanation solving part of the puzzle while breaking another. Gravitational and atmospheric dynamics were also explored, including the idea that unusual circulation patterns could trap certain gases in stable layers, preventing them from reacting as expected. While atmospheric layering can preserve disequilibrium for limited periods, maintaining it over long timescales without continuous input proved difficult to justify under the planet's radiation environment. The deeper the investigation went, the clearer it became that this was not a simple case of misclassification or observational noise. The signal was resilient, and resilience is what separates noise from phenomenon. Scientists are deeply uncomfortable with resilient anomalies because they demand attention rather than dismissal. At the same time, caution intensified, because resilient anomalies are also where premature claims can cause the most damage. Memories of past false alarms loomed large, including signals once attributed to life on Mars, Venus, and exoplanets that later dissolved under improved understanding. Those lessons shaped the tone of every discussion, reinforcing restraint and skepticism even as the mystery deepened. The phrase false positive became central because in astrobiology, false positives are not mistakes, but expected hazards, situations where lifeless chemistry imitates biological behavior closely enough to deceive even careful observers. The task was not to prove life, but to rule out every plausible non-living explanation first, a task that grows exponentially harder as data improves. With each alternative explanation weakened, the discomfort shifted subtly from doubt toward limitation, because it was no longer clear whether the problem lay in the data or in the framework used to interpret it. The models themselves began to feel strained, as though they were being asked to explain behavior outside the conditions they were built to handle. This is a dangerous moment in science, because it forces a distinction between error and ignorance. Error can be corrected, but ignorance requires expansion. As days turned into weeks and analyses accumulated, the signal remained intact, not because it was perfect, but because it survived imperfection. It did not demand belief, but it demanded respect. The question was no longer whether the signal could be dismissed outright, but whether our understanding of planetary atmospheres was sufficiently broad to explain what Webb was seeing. This realization was unsettling, because it implied that the anomaly might not disappear with better data, but might instead persist as a reminder that our definitions are provisional. At this stage, scientists became careful not just in what they said, but in how they thought, because language shapes interpretation, and interpretation shapes expectation. No claims of life were made, but the absence of claims did not erase the implication that something unfamiliar was happening. The signal had crossed a threshold, moving from curiosity to constraint, limiting how confidently scientists could rely on existing models. This did not mean those models were wrong, but it did suggest they might be incomplete, particularly when applied to environments far removed from Earth's experience. The planet, once dismissed as irrelevant, was now acting as a stress test for habitability itself, exposing the assumptions hidden within its definition. The more scientists tried to explain the signal away, the more it forced them to confront the possibility that life, or lifelike processes, may not announce themselves in ways we expect. This realization did not resolve the mystery, but it reframed it, shifting focus away from whether the signal was false and toward whether our conception of life was too narrow. That shift marks the transition into the next chapter, because once skepticism has been exhausted and the signal remains, the only responsible move left is to expand perspective, to ask not whether the planet is alive in the way Earth is alive, but whether life itself might take forms that thrive in places we once considered impossible, a question that opens the door to a far more unsettling and expansive discussion in the chapter that follows. Once the possibility that the signal could not be easily dismissed became unavoidable, scientists found themselves standing at the edge of a much larger and more uncomfortable question, which was not whether life existed on this planet, but whether their definition of life itself had quietly limited what they were capable of recognizing. For generations, the search for life beyond Earth has been guided by familiarity, not because scientists lack imagination, but because science must anchor itself to what can be tested, and Earth remains the only example where life has been confirmed. That anchoring has shaped every expectation, every model, and every filter used to decide where to look and what to ignore. Life as we know it depends on liquid water, moderate temperatures, and a delicate balance of chemistry that allows complex molecules to assemble without being destroyed faster than they can form. These requirements are not arbitrary, but derived from biology, physics, and chemistry observed under terrestrial conditions. Yet Earth itself has repeatedly demonstrated that life does not respect comfort zones, thriving in environments once considered utterly incompatible with survival. Deep beneath the ocean floor, life persists without sunlight, drawing energy from chemical reactions instead of photosynthesis. In boiling hydrothermal vents, organisms endure temperatures that would instantly kill most known life forms. In acidic lakes, alkaline springs, radioactive waste, and frozen polar deserts, biology adapts not by resisting the environment, but by exploiting it. Each of these discoveries forced scientists to expand their understanding of what life can tolerate, and each arrived only after assumptions were challenged by evidence. These extremophiles did not redefine life entirely, but they stretched its boundaries far beyond what early models allowed. The unsettling implication raised by Webb's signal is that Earth's extremophiles may not represent the outer edge of possibility, but merely the outer edge of what we have encountered so far. If life can adapt to extreme heat, pressure, radiation, and chemical hostility on Earth, then it is at least plausible that life elsewhere could arise under conditions that feel even more alien. This does not require abandoning known physics, but it does require humility about how flexible biological systems can become when shaped by different evolutionary pressures. On this planet, the environment appears hostile by Earth standards. But Earth standards may be irrelevant in a universe that offers countless combinations of energy, chemistry, and time. The signal detected by Webb does not demand a biological explanation, but it invites one as a possibility that cannot be ruled out, simply because it feels unfamiliar. It suggests that life, if it exists there, may not resemble plants, animals, or microbes as we know them, but may operate on chemical cycles that exploit energy gradients unique to that world. Such life might exist beneath thick atmospheric layers, within clouds, or in transient zones where conditions briefly align before shifting again. It might not form stable ecosystems as we understand them, but dynamic, fluctuating systems that persist through constant change. This idea is deeply unsettling because it resists visualization, and humans are most comfortable with life they can imagine. The more abstract life becomes, the harder it is to recognize, and the easier it is to dismiss. Yet science has repeatedly shown that recognition often follows discovery rather than preceding it. The challenge here is not to declare that life exists on this planet, but to acknowledge that our criteria for recognizing life may be incomplete. The chemical imbalance detected by Webb could be driven by unknown geochemical processes, but it could also be driven by metabolic-like activity, operating under rules that differ from Earth biology. The distinction matters, but it cannot be resolved with current data alone. What matters more at this stage is the realization that habitability may not be a binary condition, but a spectrum, with niches emerging in places previously written off as uniformly hostile. The planet may not be habitable in the way Earth is habitable, but it may be partially, intermittently, or differently habitable, supporting processes that blur the line between living and non-living systems. This realization destabilizes the comfortable simplicity of the habitable zone concept, which treats planets as either inside or outside a narrow band of possibility. In reality, planetary environments are complex, layered, and dynamic, capable of supporting localized stability even when global conditions are extreme. The signal from this planet may be evidence of such localized stability, a hint that something persistent is operating within a broader hostile environment. Scientists are careful here, because expanding definitions too quickly can dilute meaning and invite speculation without constraint. Yet refusing to expand them at all risks missing phenomena that do not fit established categories. This tension defines the current moment, balanced between imagination and rigor, curiosity and restraint. The planet has not proven that life exists beyond Earth, but it has proven that our confidence in where life cannot exist may be overstated. This realization does not overturn astrobiology, but it stretches it, forcing scientists to consider that life may not politely confine itself to environments that resemble our own. As this perspective takes hold, attention shifts back to the planet itself, not as a failed Earth analog, but as a unique system with its own internal logic. The next question becomes how such a world might sustain the observed chemistry without violating physical laws, whether through hidden energy sources, unusual atmospheric circulation, or internal processes we have yet to fully understand. This shift marks a transition from skepticism to exploration, because once life is no longer dismissed outright, the task becomes understanding how this planet works on its own terms. And that is where the story must go next, because to grasp the significance of Webb's signal, we must re-examine the planet itself, not through the lens of Earth-like habitability, but through the possibility that it represents an entirely different kind of environment, one that breaks the rules we thought were universal, leading directly into the next chapter, where the planet's structure and dynamics are reconsidered in a radically new way. When scientists began looking at this planet again through a different lens, something subtle but profound changed. Because instead of asking why it could not support life, they started asking how it might support something despite everything working against it. This shift did not come from optimism, but from necessity, because the signal refused to fit neatly into existing categories, and ignoring that mismatch would have been intellectually dishonest. The planet's hostility, once viewed as absolute, began to look more complex when examined layer by layer rather than as a single uniform environment. Planetary conditions are rarely evenly distributed, and even worlds that appear extreme from afar can contain gradients, pockets, and transitional zones where physics behaves differently. Scientists consider the possibility that while the planet's surface might be brutal, other regions could offer temporary or persistent stability. Thick atmospheres can shield lower layers from radiation, absorbing energy high above and allowing chemistry to proceed more gently below. Cloud decks can act as reflective barriers, moderating temperature swings and creating environments that are neither fully exposed nor fully isolated. Internal heat leaking from a planet's core can drive circulation, mixing chemicals and sustaining energy flows independent of stellar input. In such systems, lifelike processes would not need a calm surface ocean or a familiar landscape, but only a persistent energy gradient and a way to exploit it. The planet's unusual orbit, once considered a liability, now appeared potentially relevant, because eccentric or tidally locked worlds experience dynamic cycles of heating and cooling that could drive complex chemistry. A permanently lit side could power photochemical reactions, while a darker region might preserve molecules long enough to interact in unexpected ways. Atmospheric circulation could transport material between these zones, sustaining disequilibrium on a planetary scale. Scientists also revisited the idea of subsurface or atmospheric life, not as science fiction but as a logical extension of known physics. On Earth, microbial life thrives deep underground, isolated from sunlight and shielded from surface extremes, drawing energy from chemical reactions within rock. If similar processes exist elsewhere, then a planet's surface conditions may be far less relevant than previously assumed. In thick atmospheres, life could even exist within cloud layers, suspended in regions where temperature and pressure briefly align, surviving not as stable ecosystems, but as continuously cycling populations adapted to instability itself. The chemical signal Webb detected might not originate from a surface at all, but from these hidden layers, places invisible to direct observation yet capable of influencing the atmosphere as a whole. This idea unsettled scientists because it suggested that habitability is not a surface property, but a systemic one, emerging from interactions between interior, atmosphere, and energy flow. The planet, once dismissed as uniformly hostile, began to resemble a complex machine, with moving parts capable of sustaining processes that defy simple classification. This did not make life likely, but it made it plausible enough to consider seriously. The more scientists explored these possibilities, the clearer it became that the rules used to classify planets as habitable or not are blunt tools applied to finely textured realities. They are useful for sorting large datasets, but they obscure nuance, and nuance is often where discovery hides. This planet exposed that weakness because it sat comfortably in the non-habitable category, while quietly exhibiting behavior that contradicted that label. The realization was not that the planet must host life, but that the category itself might be too coarse to capture the full range of planetary behavior. This reframing did something unexpected, because it turned the planet from an anomaly into a test case, a probe into the assumptions embedded within planetary science. If this world could sustain persistent chemical imbalance under extreme conditions, then it suggested that similar processes might be operating elsewhere, unnoticed, on planets we have already ignored. The implication was not limited to one discovery, but extended to thousands of worlds cataloged and dismissed using the same criteria. The discomfort grew as scientists recognized that their filters, designed to focus attention, might also be hiding patterns that do not resemble Earth closely enough to stand out. This realization did not undermine the search for Earth-like worlds, but it expanded the search space in a way that felt both exciting and overwhelming. If habitability is not a narrow corridor but a landscape with unexpected oases, then the universe may be far more chemically and potentially biologically active than our models predict. The planet's behavior hinted that life, or lifelike chemistry, might not be rare because it is fragile, but because it is difficult to recognize when it does not announce itself in familiar ways. This idea quietly destabilized the comforting narrative that Earth occupies a privileged position simply because it sits in the right place around the right kind of star. Instead, it suggested that Earth may be one expression of a much broader set of possibilities, not the standard by which all others must be judged. As this perspective took hold, the mystery expanded rather than narrowed, because the planet was no longer an isolated puzzle, but a signal pointing toward a systemic blind spot. Scientists began asking how many other planets might be behaving similarly, quietly sustaining unexpected chemistry while escaping attention because no one thought to look. That question marked a turning point, because it shifted the focus from explaining one anomaly to reassessing an entire population of worlds. The story was no longer just about what James Webb had found, but about what it might have missed before we learned how to interpret what we were seeing. And it is that unsettling possibility, that the universe may be full of overlooked activity hiding behind our assumptions, that carries the narrative forward into the next chapter, where the implications of this discovery expand beyond a single planet and force a reconsideration of how many worlds we may have gotten wrong. When scientists began to accept that this planet might not be an isolated oddity, the implications widened dramatically, because if one world so thoroughly dismissed could still display signs of unexpected activity, then the methods used to classify thousands of others suddenly felt less secure. Modern exoplanet science is built on efficiency, on sorting vast numbers of worlds into categories that determine which deserve attention and which do not, because telescope time is limited and the universe is overwhelming in its abundance. To manage that abundance, astronomers rely on models, habitability zones, and statistical filters that prioritize planets resembling Earth in size, temperature, and stellar environment. These tools have been enormously successful, allowing scientists to identify promising candidates without drowning in data. But they also come with a hidden cost, which is that anything falling outside familiar patterns is often set aside. The signal detected by James Webb exposed the risk of that approach, because it suggested that at least some dismissed planets may be doing something interesting, something persistent, something worth understanding, even if it does not fit neatly into existing definitions of life or habitability. This realization forced scientists to revisit old catalogs with fresh eyes, not because they believed life was suddenly everywhere, but because they recognized that their criteria for interest might be too narrow. Thousands of planets previously labeled too hot, too cold, too irradiated, or too chemically unstable were classified based on surface-level assumptions, treating planets as uniform objects rather than layered systems with internal complexity. The Webb signal hinted that this simplification may hide important behavior, because planets are not static spheres, but dynamic environments shaped by circulation, chemistry, and energy flows that can create localized stability even under extreme global conditions. If one such planet could maintain chemical imbalance, then others might as well, quietly doing so beyond the reach of earlier instruments or beyond the attention of existing models. This possibility does not imply that life is common, but it does imply that activity may be more widespread than assumed, and that activity is the raw material from which lifelike processes can emerge. The discomfort of this realization lies in its scale, because it suggests that entire populations of planets may have been prematurely categorized as uninteresting, not because they were understood, but because they were inconvenient. Scientists began to ask whether the habitable zone itself, long treated as a central organizing principle, might be a useful approximation rather than a decisive boundary. On Earth, life occupies environments that would seem uninhabitable if judged only by surface averages, surviving in extremes precisely because local conditions differ from global ones. Translating that lesson to exoplanets implies that a planet's average temperature or radiation level may be less informative than the distribution of those conditions across time and space. This reframing complicates the search for life, because it replaces simple thresholds with gradients and clear categories with probabilities. Yet it also enriches the search, because it acknowledges that the universe may not optimize for simplicity or human convenience. The signal from this planet suggested that chemistry, and possibly biology, may exploit niches that appear briefly, intermittently, or deeply hidden, leaving behind atmospheric fingerprints that only sensitive instruments like Webb can detect. If that is true, then the absence of obvious biosignatures on many planets does not necessarily indicate absence of activity, but absence of recognition. This realization quietly undermines the comforting notion that life elsewhere would announce itself clearly, waiting patiently for us to notice. Instead, it suggests that lifelike processes may be subtle, messy, and easily mistaken for noise until the right tools arrive. The discovery thus reframed the role of James Webb itself, not just as a finder of answers, but as a revealer of blind spots, exposing how much of the universe remained invisible not because it was empty, but because we lacked the conceptual frameworks to interpret it. The implications extended beyond astrobiology into the philosophy of observation, reminding scientists that what we choose to look for shapes what we find, and that expectations can be as limiting as ignorance. The planet's signal became a cautionary tale about certainty, showing how confidently held assumptions can persist until confronted by data that refuses to comply. This discomfort did not weaken science, but strengthened it, because it forced a reevaluation of priorities and methods rather than a retreat into denial. Scientists began discussing how future surveys might be designed differently, how selection criteria could be expanded, and how models could incorporate a wider range of planetary behaviors without collapsing into speculation. This was not a call to abandon rigor, but to apply it more flexibly, recognizing that the universe does not owe us predictability. As these conversations unfolded, the tone of inquiry shifted subtly from exclusion to curiosity, from asking which planets could host life to asking which planets might surprise us. The signal from this one world had expanded the search space not by adding new targets, but by challenging the filters used to define relevance itself. And with that expansion came a new kind of caution, because the more possibilities are acknowledged, the more carefully claims must be framed. This tension between openness and restraint set the stage for the next chapter, because having recognized how many worlds might have been overlooked, scientists now faced a different responsibility, which was to communicate this discovery without overstating it, to balance wonder with discipline, and to explain why, despite the implications, they were being extremely careful with their words, a carefulness that becomes the focus of the chapter that follows. As the implications of the signal continued to ripple outward, one thing became immediately clear within the scientific community, which was that how this discovery was communicated mattered almost as much as the discovery itself, because history has taught astronomers that premature certainty can be as damaging as ignorance. The public imagination moves quickly, especially when the word life hovers nearby, but science moves slowly by design, not out of hesitation but out of responsibility. Every extraordinary claim in astronomy carries the weight of past false alarms, moments when excitement raced ahead of evidence and credibility paid the price. Scientists remember Mars canals, meteorites once thought to contain fossils, chemical hints on Venus that vanished under further scrutiny, and countless signals that briefly seemed alive before collapsing into mundane explanations. These memories do not discourage exploration, but they enforce discipline. In this case, discipline meant resisting the urge to label the signal as biological, no matter how tempting the parallels might appear. The data did not demand that conclusion, and scientists were careful not to offer one. Instead, they chose language that was precise, conditional, and intentionally restrained, describing the signal as intriguing, anomalous, and worthy of further investigation, but never definitive. This restraint was not an attempt to hide excitement, but an acknowledgement of uncertainty, because Webb's observations, as powerful as they are, provide only a partial glimpse into a complex system. Atmospheric spectra offer clues, not confessions, and interpreting those clues requires context that cannot yet be fully reconstructed. The planet remains distant, unresolved, and inaccessible, its environment inferred rather than observed directly. Scientists understand that a single dataset, no matter how robust, cannot carry the burden of proof for life beyond Earth. They also understand that words shape expectation, and expectation shapes interpretation, both within the scientific community and beyond it. This is why press releases were cautious, papers were carefully worded, and interviews avoided speculation, even as curiosity grew. The goal was not to dampen wonder, but to protect it from collapsing under its own weight. At the same time, restraint does not mean dismissal, and the careful tone adopted by scientists should not be mistaken for indifference. Behind closed doors, the signal sparked intense discussion, planning, and anticipation, because the absence of a claim does not erase the presence of a mystery. Scientists know that the most transformative discoveries often begin quietly, wrapped in cautious language, and unfold over years rather than headlines. This moment felt like the beginning of such a process, not because life had been found, but because assumptions had been challenged in a way that could not be easily reversed. The decision to be careful was also strategic, because the next steps matter more than the initial interpretation. Follow-up observations, independent verification, and deeper analysis are the only paths forward, and those paths take time. Scientists must wait for additional Webb observation windows, refine atmospheric models, and potentially involve future instruments capable of probing the planet in different ways. Each step reduces uncertainty, but none eliminate it entirely. This slow progression can be frustrating to those eager for answers, but it is the only way to ensure that when conclusions are eventually drawn, they are earned rather than imagined. The care taken now is an investment in credibility later. This is why scientists speak not of discovery but of signals, not of life but of chemistry, not of conclusions but of possibilities. The signal sits in a liminal space, neither dismissed nor embraced, waiting for evidence to tip the balance. That waiting is not passive, but active, filled with preparation and refinement, because the universe does not always repeat itself on command. Scientists know they may only get a few chances to observe this planet under the right conditions, and each observation must be planned meticulously. The caution also reflects an understanding that even if the signal eventually proves non-biological, it will still be profoundly important, because it reveals behavior that models failed to predict. Either outcome reshapes understanding, which is why restraint and curiosity coexist rather than compete. As the scientific community holds this tension, one thing remains certain, which is that this story is not finished. The signal has not delivered an answer, but it has asked a question powerful enough to reorganize priorities and sharpen attention. And it is precisely this unanswered state, this deliberate pause between observation and interpretation, that leads into the final chapter. Because what matters now is not what has already been seen, but what comes next, and what the universe might reveal if this signal holds under further scrutiny. What happens next is where this story truly matters, because the signal detected by James Webb does not demand belief, but it demands patience, and patience is where the future of this mystery lives. The planet remains distant, unresolved and stubbornly silent beyond the chemistry written into its atmosphere, and that silence is not empty, but expectant. Scientists now face a waiting game shaped by orbital timing, telescope scheduling, and the slow accumulation of evidence, because Webb cannot simply stare endlessly at one world without sacrificing countless others also waiting to be understood. Follow-up observations must be carefully chosen, timed to capture the planet under different stellar conditions, different phases of its orbit, and different atmospheric states, each offering another fragment of context. If the signal persists across time, across observational angles, and across independent analyses, its credibility will strengthen not through repetition, but through resilience. If it fades, changes, or resolves into something more ordinary, it will still have served a purpose by exposing the limits of expectation and refining the tools used to search for meaning in distant light. Not to force the signal into existing frameworks, but to explore possibilities that current frameworks cannot yet accommodate. This is how science evolves, not through revelation, but through revision, guided by evidence that refuses to disappear. What makes this moment special is not the possibility that life exists on this planet, but the realization that life, if it exists elsewhere, may not announce itself in ways we are prepared to recognize. The universe may be quieter, subtler, and stranger than our stories allow, hiding activity in places that look wrong from a distance and only reveal themselves when observed with enough humility. The signal from this planet reminds us that absence of familiarity is not absence of meaning, and that the line between living and non-living systems may blur under conditions we have barely begun to explore. It reframes the search for life as not just a hunt for mirrors of Earth, but as an exercise in learning how little we truly know about what life can be. This does not diminish Earth's uniqueness, but it places it within a broader, more mysterious context, where uniqueness does not imply exclusivity. As the story closes for now, the most important takeaway is not that life has been found, but that certainty has been weakened, and weakened certainty is where discovery thrives. James Webb did not confirm that we are not alone, but it challenged the confidence with which we once said where we must be alone. The planet that should not be habitable has not revealed its secrets, but it has revealed our assumptions, and that may be the more valuable discovery. The universe has a way of teaching patience by withholding answers just long enough to expand the questions, and this signal feels like one of those lessons. Somewhere, far beyond direct reach, a world continues to orbit its star, maintaining chemistry that refuses to behave, quietly indifferent to our categories and definitions. Whether that chemistry is driven by exotic physics, unfamiliar geology, or something that edges closer to biology remains unknown. And that unknown is not a failure, but an invitation. An invitation to observe more carefully, to model more honestly, and to accept that the universe does not owe us clarity on our timeline. For now, the signal remains, suspended between explanation and mystery, reminding us that the most profound discoveries often begin not with answers, but with discomfort. And as James Webb continues to unfold the universe layer by layer, one truth becomes impossible to ignore, which is that the cosmos is not just larger than we imagined, but more flexible, more surprising, and more willing to challenge our certainty than we ever expected, and that whatever life may be, wherever it may exist, it will likely arrive not as a declaration, but as a quiet signal that forces us to listen more closely than we ever have before.